Now what I've done here is started to draw a sketch now for this next part of the question, where we're told that the particle P then comes to instantaneous rest at this point C on the plane, and BC is 1.5 meters. Now from B to C we're also told that it's rough, and the coefficient of friction between P and the plane is mu. So we've got to use the work energy principle to find the value of the coefficient of friction mu. Well, you can see I've also updated this diagram with the speed that it passes through the point B, 5 meters per second. We were told that in the very first part. So using this work energy principle, what's that all about? Well, essentially we're going to be looking at the work done against friction equals the loss in kinetic energy minus the gain in gravitational potential energy. I'll run through that part later on, but for the moment, because we're dealing with friction, we need to start marking some forces on our particle. So this is a general position between B and C then. What forces have we got acting on our particle? Well, we've clearly got the weight that acts downwards. Okay, so we'll just mark that in. mg. Mass is 0.5, so it's going to be 0.5 g newtons. There's going to be a normal contact force from the plane, which we'll mark in r newtons. And we've got the frictional force opposing motion, so because it's going up the plane, obviously friction then acts down the plane, and it will have reached its limiting point, so that will be mu r. Let's just write that in then in here as mu r newtons. And when I'm working on planes, what I want to do is always draw a dotted line in there, and we can mark in that this angle in here is the same as the angle of the plane, 30 degrees. So because we're going to be dealing with this frictional force here, which contains R, I'm obviously going to need to get R first of all. So to do that, what I'm going to do then is resolve perpendicular to the plane. So we've got all of R acting outwards, minus the component of weight into the plane, which is going to be minus 0.5 g cosine of 30 degrees. Obviously the mu r doesn't come into play here because it's perpendicular to this direction. So this is our resultant force. It's in relative equilibrium to the plane in this sense, so therefore that resultant force equals 0. And if we rearrange this, we end up with r equaling 0.5 g being 9.8 times the cosine of 30 degrees. You could leave it like that, or you could work it out. If you do, it's going to come out at 4.2435 and so on newtons. Okay, so that's given us the normal contact force R. Okay. Now I did say we're going to have to use this work energy principle. So we've got to look then at the work done against friction. So let's just set up this equation first of all in words. We've got the work done against friction. Okay, work done against friction. And what is this going to equal? Well, originally it had kinetic energy here. This is where it had all of its energy, kinetic energy. So as it went up the plane, it lost kinetic energy. So we've got to look at the loss in KE, kinetic energy. And as it lost kinetic energy, it gained gravitational potential energy. So the work done against friction is going to equal the loss in kinetic energy minus what it gained in gravitational potential energy, GPE. Now we can start to set this up as an equation. So when it comes to the work done against friction, that's going to be force times the distance that this frictional force moved, its point of application. So it's going to be all of mu r multiplied by the distance BC, 1.5 meters. So we therefore have that mu multiplied by r, I'm just going to put that value in there. You could leave it though as just r, it's up to you. But we've got mu r 4.2435 and so on, multiplied by the distance moved, this is our force, times distance moved, 1.5 meters. Okay, so that's the work done against friction. Now we need to look at the loss in kinetic energy. Well, the kinetic energy at the beginning would be a half mv squared, so it's half the mass is 0.5, times v squared, 5 squared. It had no kinetic energy at the end, so it would be subtract 0 if you like, but it just leaves us with this value. Now we need to look at the gain in gravitational potential energy, mgh. We know m, it is 0.5. We know g, it's 9.8. But what we don't know is how high it rises as it goes from B to C. So we need to get that height, and again we can just turn to drawing a triangle which represents B to C on the hypotenuse. We'll just put that in there, B to C. We know that's 1.5 meters. We've got this angle in here of 30 degrees, and we're out to find that distance h up there. So we should know then that to do that, opposite over hypotenuse by basic trigonometry, so that's going to be the sine of 30 degrees equals the opposite side h over the hypotenuse 1.5. Rearrange this for h by multiplying both sides by 1.5, and you therefore have that h equals 1.5 multiplied by the sine of 30 degrees. Sine of 30 is a half, 1.5 times a half gives you 0.75. 0.75 then meters will be that height h. So minus the gain in gravitational potential energy minus mgh. So we now know h, it's 0.75. Okay, so we've got everything now in this equation here in order to find out what mu is. So to do this, many ways you can do it. What am I going to do? Well, I think I'll multiply these two together first of all. If you do that, you end up with 6.3652 and so on, and that's multiplied by mu, and that equals, well, if you work all of this side out, you end up with exactly 2.575. So to get mu, then obviously we need to just divide both sides by 6.3652 and so on. So 6.3652 and so on. What we end up with is 0.4045 and so on. And if you round this to, say, two significant figures, you end up with 0.40 to 2SF. Two significant figures. Okay, so there's your value of the coefficient of friction.